Welcome to Math with EJD. In this video, we'll continue to talk about characteristic equations for homogeneous linear second order ordinary differential equations. In the last video, I had introduced us to the idea of second order ordinary differential equations, and then we distinguished between homogeneous and non-homogeneous. Um, okay, so here we are focusing on how to solve homogeneous equations. So a homogeneous linear second order differential equation takes the form ay prime prime. I give you a particular form previously, so that also stops. That also holds. So ay prime prime plus by prime plus cy equals 0. Okay. So in this situation, this is a nice way of representing the same thing. So here, where a, b, c are constants, they are constants. So the solution The solution depends on the roots of the characteristic equation. So these are the characteristic equation thing is coming from. On the roots of the characteristic equation. So the characteristic equation is based on that expression up there, and that is a r squared plus br plus c equals 0. So you may be wondering, how do we come about this? Okay, so imagine that we have okay, I guess I want to stay a bit on that. So for ay prime prime plus by prime plus cy equals 0. Okay, let's so that's the equation, right? For this now. So if imagine that you let the solution y to be the same thing as e raised to power um, say r x, okay? Because y is a function of x. So let the solution be e raised to power rx. So, it means you already have this, right? The next thing is you can also have y prime, which is when you differentiate this now, you have r e raised to power rx. If you have y prime prime, that is r squared e raised to power rx, right? R squared e raised to power rx. So if you plug all of that into this, what do you get? So you have a into r squared e raised to power r squared e raised to power rx plus b into r e raised to power rx, okay, plus c e raised to power rx equals 0. So you can see that rx is common all the way, right? E raised to power rx is common. So you can take e raised to power rx out. So you have e raised to power rx into ar squared plus br plus c equals 0. Okay. So from there, you can divide through by e raised to power rx, and then you have ar squared plus br plus c equals 0. And that is why this becomes the characteristic equation that you have here, right? So that's how that is arrived at. So the nature of the solution, like we said, depends on this characteristic equation. So we have different cases. Um, so we have case one. So case one is that we have, so this is a quadratic expression for sure. So we can have two real distinct roots, two real distinct roots. Okay. We have two real distinct roots. So characteristic equation, if the characteristic equation has two real and distinct roots and distinct roots R1 and R2. So the general solution is y of t equals c1 e raised power r1t plus c2 e raised power r2t. Okay, this is like the solution if you get two unique characteristic values of r, right? That's case one. And for case two, so case two, we have, so in this case now, we have an example. We solve y prime prime minus 3y prime plus 2y equals 0. Okay? So so to solve this, of course, we already know uh the characteristic equation, the characteristic equation is r squared minus 3r plus 2 equals 0. Okay? So I mean to factorize this now, this is just r squared minus well, not to waste time, right? I mean, this is simply r minus 1, r minus 2. So factorization shouldn't be a problem, I believe. So that we have r1 to be 1 and r2 is equal to 2. So since we have this now, we can now have the general solution. Okay. So we have the general solution would have to be y of t equals C1 e raised to power RT. So R1T, right? That's R1T plus C2 e raised to power R2T. And just like we have, right? That means that y of t is equal to C1 e raised to power t. That's 1t. Then C2 e raised to power 2t. So that's the solution in that case. All right. So we have unique values 1 and 2 in this case. So that is example 1, right? That's example 1. We can now go for case two. Case two, what if the when you solve the characteristic equation, you get repeated roots, which is also possible, right? So you can get repeated roots. So if the characteristic equation has a double root r, the general solution takes a bit of modification. The general solution is y of t equals c1 plus c2t e raised to power rt. So instead of having c1 e raised to power rt plus c2 e raised to power rt, having a repetition, then the second one, okay, in fact, let me write it gently so you can get it. So y of t is now c1 e raised to power rt plus C2, normally it should be C2 e raised by RT, right? But because that R is still is still the same R, so to distinguish it from the first one, then we now multiply by the dependent variable. So if the dependent variable was X, we'll put X there. But if what we are doing is, what we have is Y of T. Let me see what the question. Okay, here we have assumed that it's based on t. So if it's based on x, we use x in place of t. So because they are the same, so you have c1 e raised power rt plus c2 t e raised power rt. So this t now distinguishes this from the first one, so that overall your y of t is now c1 plus c2 t multiplied by e raised power rt. So this is when you have repeated roots. Okay. Now we can take an example in that regard. Example 2. So example 2, we need to solve y prime prime minus 4y prime plus 4y equals 0. Okay? So we know that the characteristic equation is r squared minus 4r plus 4 equals 0. If you factorize this, you have r minus 2 squared equals 0. So it means you have double roots, okay? So you have r equals to twice. That's the idea of double roots. So r is minus 2, r is minus 2. I mean, r is 2, r is 2. So we have double roots, r equals 2. So the general solution, so the general solution is y of t equals C1 plus C2t into e raised power 2t because R is e raised power 2t. So this is our general solution in this case. Okay, so let's go for case 3. Case 3, another possibility when we solve quadratic equation is we can get complex roots. We can get complex roots. So if the characteristic equation, if the characteristic equation, okay, has complex complex conjugate roots, complex conjugate roots, and that's something like R equals alpha plus or minus IB. All right. So this I makes it complex. So the general solution is y of t equals e raised power alpha t. So this alpha, so that's e raised power alpha t into C1. So this makes it so you are going to have a kind of oscillation. Okay. So you have e raised power alpha t, then C1 cos beta t, this beta here, then plus C2 sine beta t. Okay. So so when you have complex results, that's what exactly happens in that situation. Okay. So if the result is complex, that if you get complex root from the characteristic equation. So let's take an example that deals with that. So example three, you need to solve y prime prime plus y equals 0. Okay. So again, the characteristic equation, the characteristic equation is r squared plus 1, based on what we have, and that is equal to 0. So that means r squared is equal to plus or minus r alone rather is equal to plus or minus I. So that's like so if you like, that's like 0 plus or minus 1I. Okay, for better understanding. So normally this 0 now is like your alpha. We should now be e raised power 0t, and e raised power 0 is 1, so we don't have to worry about that. So we are only bothered about the inside where beta is now 1. So with that now, we can say that we can say so the general solution, so the general solution is y of t equals C1 cos 1t, that's C1 cos t plus C2 sine 1t because beta is t. So this is the general solution in that situation. So again, some applications of this would be in areas like in physics, you have it in harmonic oscillators for springs and pendulums with solutions involving sine and cosine. Then you have electrical engineering. Uh, you have LC circuits where charge and current oscillate, and you have mechanical vibrations. That's structural analysis of beams and bridges. So you have such applications here. So in this case, we can take practice questions. So let's take some practice questions. So, solve the following. Solve the following. 1, you have y prime prime plus 4y prime minus 21y equals 0. 2, y prime prime plus 10y prime plus 25y equals 0. 3, you have y prime prime plus 6y prime plus 13y equals 0. Then number 4, you have y 4. You have y prime prime minus 2y prime minus 3y equals 0. 5, you have y prime prime plus 2y prime plus 5y equals 0. Then, of course, we have some involving initial conditions. So y prime prime minus 6y prime plus 8y equals 0. So you now have y of 0 equals 2, and then y prime of 0 equals 3. So it means you can apply this to get rid of the constants C1 and C2. Then another one in that line would be 7, where you have y prime prime minus 2y prime plus 2y equals 0. And then you still have initial conditions. Y of 0 equals 1, and y prime of 0 equals 0. Okay. So with this in place now, you should have a very good understanding of characteristic equation method for solving homogeneous, nonlinear, second order ordinary differential equations. So feel free to let me see your answers in the comments, either on Facebook or on YouTube. Okay. Also, let me know if there's a topic you'd like to teach or a problem you'd like me to solve in the comment. And if you have not subscribed, you'll be missing out, because after now I'll be talking about non-homogeneous equations that will involve three methods. I think I'll make them in separate videos. The first would be undetermined coefficients, followed by D operators, and then variation of parameters. So you don't want to miss any of that. So subscribe and hit the notification bell so you can always get alerted each time a new video is released. If you have subscribed already, thank you very much. Don't forget to like and share also, so that more people can have access to this great content. Till I come your way again, keep doing math right. Bye.